Good morning, everyone. My name is René Hagen, René Hagen in English, and I have the honor to welcome you. And it's a kind of special welcome because it's a kind of welcome and a kind of goodbye. I'd like to explain to you. This is me. And why do I show you this picture? This is me joining the fire service in 1978, 44 years ago. For some colleagues have a good look, I was slim at that time. And I show you that because last week was my last day working for the fire service. I decided to stop working with the fire service on a daily basis. I find after 44 years it was enough. But that also includes that this is my last Fire Safety Science Conference, which I organized all those 13 previous times. And my colleagues asked me, and especially the conference committee, they asked me, what can we do for you after 14 Fire Safety Science Congresses? You can't say just hello and not be there today, because that was my original plan. And I was thinking about that. And then I was thinking about fire safety. I'm not fire safety. I'm just a very, very, very small part of it. So it's not up to me to have a big celebration with my goodbye. I did this work for 44 years, and sometimes people ask me, did you enjoy it always? No, I didn't enjoy it always. But every day it was worth doing this work. And you all recognize, because you're also working in the field of fire safety, if it's as a firefighter, or is it from a consultancy, or for research, or whatever it is. So then I start thinking about fire safety. Fire safety is not about legislation. It's a very small part, but it's not. Fire safety is not about policy. Although my work the last years was only policy driven. It's not about figures and data. Those are numbers. Fire safety is not about numbers. It's not about engineering. And I know what I'm saying now on a Fire Safety Science Conference with all those fire safety engineers, but it's not only about engineering. It's more than that. It's not about codes. It's not about building materials. It's not about modeling. Not about installations. Not about testing. Not about a lot of things. But what is it about? That's what I was thinking when I was invited to be here now on the stage. Fire safety is about people with names. Sanne, this is Sanne. And what we are doing, this is Sharon. Sanne is the next one. Okay. Yeah, I had to start all over again. It's about people. What we are doing, we all, is prevent people from those burns. That is why we are working on testing, on codes, on building materials, on fire safety engineering, at the end on firefighting, and after that, about the burn scare. We all are working to avoid this. It's about people. And I care about people, and I think we all care about people, and that's the essence of the work we are doing. Of course, we like calculations, mathematics, and whatever it is, the fire dynamics and whatever, but it's about people. And we can't do this work without caring about people. And we were talking about fatal fires, and we said, oh, Netherlands, we're doing quite well. We only have 35. Yes, but there's 35 of people who didn't survive it, and it's much more people, 10 times more, suffering those injuries. Scars for the life long. And I think that is the reason I did this work for 44 years. And it's not only about me, it's about we all. we all doing this work to prevent these kind of things. Back to the question. But the question was asked to me, what do you want? What do you want getting here? I like whiskey, so this was the easiest. Give me a bottle of fine whiskey. That's no problem. And I was thinking, I said, I know what I want. I know the present I want from the Fire Safety and Science conferences. And at the same time, I like to give that present to the Fire Safety and Science conference. To you all, and a lot of you are here there for many, many times, some even 14 times. You are coming here to be better in your work. And I like to give you a present for that. My present is to put these people highlight those people, putting them in the picture. And that is what I'm going to do the next 2 days. And how I'm going to do that? With an exhibition. 3 years ago, that was too early. 3 years ago, this exhibition was held by the European Fire Safety Alliance in the Parliament, the European Parliament. And I spoke a lot of members of parliaments, and they said, we have exhibitions in our parliament every week, through the whole year. And this one is by far the most impressive we ever seen. And it is. I found it is. And this is what I want to give to you. That means all those heroes, we will show you. En nog een klik. And another click. It's coming, it's coming. Now I have 5 minutes, so I have time enough. So, who made this? Oh, I did. I think it's those heroes, and we have, there is an exhibition with 30 pictures we have here, 30 big pictures about those heroes. And that exhibition I want to open now, and please have a look the coming 2 days. It's here in the room next to it. And there's always a beautiful book for everyone of you with all those pictures and all those stories of all those heroes. And here to remind us on why we are doing this work. And the last one is open. Thank you. I would like to introduce the chair of today. Tomorrow we have another chair. Patrick van Hees from the Lund University in Sweden. And we are very happy that he will chairing today and even give tomorrow a lecture. So we'll see you 2 days. We know each other quite a long time. And it's always easy to speak Dutch to you because you're original from Belgium. But I heard you this morning speaking in the backside of my car, speaking Swedish. You're doing this quite well. Thank you. Yeah? I didn't understand anything, so I suppose it was quite well. But for today, from now on, the floor is yours.
Okay, thank you. And thank you for your opening speech. And I think it's now not easy to change after such a kind of emotional period. But I hope now this one works. Yeah, good. So I also would like to welcome all to this conference. I would like to thank the organization for inviting me here to be the, let's say, day chair for today and to give a presentation tomorrow. And I feel a bit nervous because it's almost 2.5 years ago that I've been at a conference and even been chairing a conference. So it's almost like you're starting a new career. I don't know how you feel here to see each other and to meet each other. I think this is fantastic that's how it is, because this is, like René said, it's about people and meeting people. And it's nice to have this kind of box, which is called Zoom, but it's not the same. I think it's very good that we are now in another period, and I'm happy to see even a few students of Ghent here, which I have not seen in life. So to see them here finally. So yeah, but let's forget about this COVID and let's focus on good things. But in fact, if I go back 2 years and a half, the latest conference was in fact this one I attended. So I think that's quite nice to say. So it's nice to see you all again. There's only one condition. I didn't say that when I accepted the invitation, but I'm going to say it now. We don't talk about football today and tomorrow. So it's quite important, I think, for me. I thought I could come here in a Belgian shirt, but I decided not to do that. But you were better, so anyhow. So that's a little bit the major, let's say, introduction. And I want to show a few slides as an introduction to the conference, and also to have it as a red thread, so you can, during the days, think about that. This is the history, a bit what I've seen, at least when I look to Sweden. We started with big city fires. I think I have a list with maybe almost 15 big city fires in Sweden in the Middle Ages, or in the late Middle Ages. We tried to solve that by making districts, but that didn't work as well. So we said, okay, we still have house fires. We don't want to have the house fires, so we make regulations. I'm not going to go into the ways how we did every step to reduce it. And then we say the houses aren't enough. We need to have compartment fires, and we keep them inside a so-called fire compartment. But we see that maybe that's in order to reduce this, both fatalities, but also, as René showed very well, those people who are injured and having to suffer with that all their life. We are coming into fires in a single room and try to limit that and to solve that. And that's a big challenge. So we have for us. We come into personal integrity items and so on. So it's a long list, and I'm not going to talk even too much to take time from the other speakers, but that's where we are if we look at from the history. And we have at the other time, the today and maybe the future. We have very innovative buildings, high-rise buildings, multifunctional. There's hardly an airport where there's a train station, a hotel, conference center, and all these things. They are very complicated, and we have to solve that. We have green buildings, and I made this picture here to the right where you have it's a greenhouse, a house with a green building then, not a greenhouse, that's something else, where you have solar panels, you have batteries in it, and everything around that. And so we have suddenly a different situation. And think about this, again, this idea on trying to keep it inside maybe a room or in a fire compartment. We have digitalization gets more and more. It is kindly an aid to us, but it's also maybe a threat for us if these things are not working. And we have new threats. When I made this presentation a year or two ago at the conference also, we talked a lot about these called antagonistic attacks. Now we all know that after COVID we came into another safety position where we don't know what's really happening sometimes. We get very bad feelings, if you see, with the safety and security on a military front, and we need to cover that because the fire safety needs to tackle that also. And everything becomes more and more complex. And I will talk about that. And this is a little bit an introduction to tomorrow, so I have extra 5 minutes tomorrow. So that's the trick. So that's a little bit the introduction. So think a little bit about the history, how we go towards protecting, let us say, the single room, and also thinking about some of these. This is not a full list. It's just some ideas what we have and which maybe pops up today, and how we have people have to solve this, and also how the fire rescue service have to deal with these things, which are always changing, and so on. And we sometimes, and now maybe I'm very honest, I think we sometimes always one step behind with all the innovations and the technology and then the fire safety. Okay, well, by the way, there's maybe a problem with the batteries in the cars and so on, but there are already thousands of them. But I don't want to just point out of that. There's a lot of things. So if we see then now to the conference, a little bit practical things. We have this morning, let's say, in this auditorium, all the presentations, starting with Andrea, and then we have a break, 11:05, 11:30. Try to, now to be a little bit the police, try to be back in time, so don't hang around outside, come back. I'll try to get the speakers also keeping their time, so because that's important. Then Ricardo will take over, and Ruth, and around 1 o'clock we have lunch. The lunch is 3/4 of an hour, rather short maybe, but try also to come back at that. The lunch is both in the hall, this floor, and also in the lobby, so you try to find where there's place. Don't queue where there's the biggest queue, go to the other queue, which is maybe even bigger. So, but I think that's certainly possible for all of you. Then after lunch, we start with so-called breakouts. I'm telling you this, you should have this on this paper. So you have the breakout sessions. There are 4 of them. I learned that it was very easy to get it, so you go out that door, and then most of them are in that area. And if you don't see them, then you just go around and around and around until you find it. So I think that's important. So you will manage that. I was also asked to tell you that the time here between 3 and 2:45 is really to change between 2 rooms. So you can grab a cup of coffee, take it in, don't take it in the rooms, I learned. But try to use that time to move from one room to another during this change of breakout sessions. On your badge, you can see what you have registered for. I learned from the organization that if you suddenly say, okay, I want to hear my colleague from Sweden, Lars, rather than to listen to somebody else. I'm not going to say who, because then I thought that maybe that's not good. So it's always the positive thing I try to do. Then it's possible for you to do that change. So if not everybody suddenly decides that. So I think that's, and then the most important thing is that we decided to have think about my slides on history and new threats, to do kind of a wrap-up where we will tell a little bit, okay, what's done today now, so that we'll come back here at 4:30 at the latest, so you will be informed when the time is in the different workout sessions, and then you come back to here in the Brouwerzaal. And then after that, there is some network drinks. There's a bit of a difference, green and lanyard, or what is it? Green lanyard, so, and white. I have this white one. I don't know what that means, if I get food or not, but I've been promised that I will get food. So, but anyhow, the green ones are those who have registered for the barbecue afterwards. So, and certainly will enjoy that. I see that now my time is over, and I hope I had covered everything. Okay, the exhibition, the most important thing, I think if I understand, then you have to take that door and somewhere under that part. I see that I have everything now, so I will introduce the first speaker, which is Andrea Lucherini, which I met live half a year ago for the first time in Ghent, because he has been working both in Belgium, at Ghent University, also at the University of Queensland in Australia, and Denmark, Technical University. And now recently he been appointed to the position of senior researcher at the Slovenian National Building and Civil Engineering Institute, which is shortly named ZAC. It's a bit easier. And I heard this morning also that you recently been granted a Marie Curie postdoc research funds with Ghent and Edinburgh, so very nice. He works a lot on construction materials engineering with specialization on fire safety science and engineering. So the floor is yours, Andrea. Good luck.
Thank you.
And enjoy your conference.
Okay. I prepare some water just in case. Okay. Okay. Good morning, everybody, and thank you very much, Patrick, for the introduction. As just Patrick introduced, I'm Andrea Lucherini. Maybe as you can guess from my name, maybe we're expecting a female, but I'm Italian, and in Italy this name is very well used for a male person. But that's it. I'm here to represent and today to discuss about the analysis and the numerical simulation of multi-compartment fire tests for fire safety of healthcare facilities. And the presentation is something that I did during my postdoc at Ghent University, not too far from here, where I carried out like different simulations and analyses on the different compartments. And first of all, it's a pleasure for me to be here today because, after 2 years of no conferences, it's a pleasure to be here and to discuss also about this research, because this research was mainly carried out during lockdown or the COVID years. So it's very good today to sit down here and get any feedback. And if you have any questions about any aspect, please feel free to reach me at the end of the presentation. Hopefully there'll be enough time, but also during the conference these days I'll be around, so I'll be very happy to discuss about that. So this wrong one. So just to introduce the presentation, and the whole project itself focuses on the fact that there are new architectural trends, and one of the architectural trends in the building industry is to promote this sort of openness and interaction in different areas and different building areas. And what you can see here, for example, in the case of healthcare facilities, which is what we studied and we focus on, here is just, is an open area which is along a corridor. So what is important is that by having common areas where people can interact and they can have a sitting, can have a coffee, or they can have food, but it's very important that there is this new concept of pushing to have open areas and to have shared areas where people can meet. And thus, for the case of fire safety, it's very important because you can have a very important change in the way we consider evacuations and the problem of fire safety and a fire hazard within a building. Because what we did in the past, this is the traditional configuration when you have we have compartments, you have rooms, and you have a common area, and you have stairs for evacuation. What you can imagine is that if you have a fire in a room, what people will do, will try to escape and go into the corridor. Corridor usually is a low fuel load areas, and people can evacuate, and the fire, according to compartmentation, should be contained within the compartment of fire region. And then if you have, in the case of a fire in a common area, what you would do, the person in the rooms can still go into the corridor and escape, and the fire, again, is meant to be contained within the compartment of fire origin. In the new case of a new open area, where you have rooms, different rooms, but then you have a big common area within the evacuation routes or along the evacuation routes. What you can see, if you have a room with a fire, then you can see that again people can escape and go reach the stairs and go to a safe place. But what happens in the case of if you have a room and people have to evacuate and the fire will be along the evacuation route? So this completely changes the fire safety strategy, and we might have a problem because we might have a fire hazard, so people exposed to critical conditions along the evacuation routes, which is usually we design and we think they're safe. So what we did with different partners at the university and also institute, we started looking into the case of fire safety in healthcare facilities, and particularly to look into how different active fire protection systems, so for example, detection, smoke extraction, extinction, different kind of doors, can have an influence on the evacuation routes and different strategies, particularly related to evacuation strategies. So if we can have, like, stay put, or you can have like a horizontal, vertical evacuation within different floors. Well, what's important within the building and the healthcare facility is important to understand what are the occupants and what kind of occupants we have within the building, because the fire safety strategy, again, has to represent and be in line with the people that are within the building. And for example, in terms of occupants, are the occupants self-reliant? Are they sleeping? And also, in terms of staff, is the staff trained? And for example, during night or the day, what is the amount of staff that will be available within the building that can help within the evacuation strategy? So what we did is, maybe in the past you've heard about like the VIPA 1 study that was carried out years ago, but then this is a continuation of VIPA 2 and VIPA 3 are a continuation of this big project that in general focuses in this new problem of having open configuration that would represent a potential fire hazard along evacuation routes. And the project focuses on examining the effectiveness of various fire safety measures, define an assessment framework, evacuation framework, to understand how different fire safety measures and combinations can be combined with different evacuation strategies. And in terms of research strategy, what we did first, there are some to do some experiments, so investigate the effects of fire safety measures in laboratory conditions first, analyze these informations also using CFD simulations, carried out additional fire safety CFD simulation to understand how different scenarios can change the variables of the study, and finally define a framework for healthcare facilities. So just to give a bit of context and what happened at the beginning, the study number 1, so this was carried out in 2015. So at the beginning, there were like some large-scale tests that were carried out at Ghent and Warrington Fire in Ghent. So this is the first case, which is like a multi-compartment facility when you have a big common area, which is about 130 square meters. Then you have 2 evacuation corridors with a single door or a double door, and you have rooms connected to the evacuation corridors. And what was studied here, there was a fire scenario, fire hazard, which was in this case a 2-seat couch. And what they did 5 different tests. Then the first test would be not having any fire safety measure. Then they look into other 4 tests, and they start looking at the different combinations and how the smoke spread and fire dynamics would change in the case of different fire safety measures. The first one would be using fire-resistant doors at the beginning of the corridors. The second one is to use a smoke extraction with both supply and extraction mechanical. The third one was to use a sprinkler within the room, the common area. And the fifth one was to use the combination between sprinklers and more smoke extraction. Of course, their research outcomes came out and also were published, and I'm going to give you like a bit of context later where you can find this sort of information. But also going to move into the VIPA number 2, which was carried out in 2020. Again, a very similar configuration where they have the same common area. You can see here, 130 square meter. Then you have a couch, again on fire, 2-seat couch. And then you have the same corridors, but in this case, we look at how the having 2 rooms adjacent to the common area would be affected by the fire dynamics in the common area. So you have test number 1, again, not having any measure. The 2-seat couch is on fire, and then you see the fire dynamics within the compartment. Looking into, for example, what is the difference between these 2 rooms? Here we have a smoke-rated door, and here you have a fire-rated door. And to see what are the outcomes and how the fire dynamics would change within the compartment. Then again, a series of tests. Then they start looking into test number 2. They start using a combination on having a fire curtain that would go down to 0.9 meters and a mechanical smoke extraction with openings that would provide natural ventilation supply. Then you have test number 3, which is the same screen, but instead of leaving like 1 meter, more or less 1 meter above the ground, then it was taken all the way down as soon as the fire alarm was triggered, and then with, again, extraction. Then they use also the same configuration, but in this case they have a smoke extraction that the flow rate would change based on the pressure difference within the compartment. And the last one would be a smoke extraction in combination with the sprinkler systems. So what is important is that what is key here is that which sort of fire scenario we've been considering. So the fire scenario that was representative of this study, it was selected, it was a 2-seat couch that, of these dimensions with ignition on the corner using some heptane-soaked low-density fiberboards. And what you can see here is that the couch was first, before the experiments, was burned within in a laboratory in a calorimetry hood. That mainly you can see how the fire would spread within the couch and what is the evolution in time of the heat release rate of the couch in these specific conditions. So in particular, what I just wanted to highlight is that if you compare to the typical alpha T-square fires that we use for design purposes, you can see that the couch would be a very similar alpha T, it would grow as a very similarly to alpha T-square medium fire, and with a peak heat release rate of about 800 kilowatt. Today, I'm not going to go too much into detail about the experimental results because there is here engineer Pope that is gonna be part of one of the workshop later. So, but in general, they got like a lot of experimental data in terms of thermocouples and thermocouple trees, pressure gauges within the compartment, heat flux gauges, gas analysis, so how the gases were within the compartment, and also video cameras to look at the smoke movement. And if you have more information, I would advise you to go and attend innovative application of smoke control in residential care buildings. That is part of the breakout sections on this afternoon, I believe. So what I'm going to discuss this morning is instead about the CFD simulations, because what we did, of course, when you do large-scale experiments, they're always like time-consuming, resource-consuming. So what is important is that we get a first understanding of few scenarios that we studied, and then we go into simulations, and we try to understand by changing different variables what would be the new outcome. And so the objective of the CFD simulation would be to validate first the CFD simulations based on the experimental results just found, then interpret the performance of large-scale experiments, because in the large-scale experiment we got certain data, but if we validate our simulation, we can get a different information within the compartment. That you can see here, there's information we can get like the fire, the smoke movement, the temperature within different planes within the compartment. So we wanted to analyze other scenarios, and I'm going to discuss which scenarios we evaluated. And in terms of the assessment parameters, we look into the smoke movement and distribution, visibility, flow fields, so in terms of speed of gases within the compartment, temperature, and fire-induced pressure. So we used a software that is well known and well used within the research, but also the practice, and it's called Fire Dynamics Simulators, FDS, with the version that is written here, which is developed by NIST, the National Institute of Standard Technology of the United States, Department of Commerce. So it's an open access, open source computational fluid dynamic, particularly focused on fire-driven flows, with emphasis on smoke and heat transfer. And this is very well known and used within the practice to solve both fundamental and very basic problems, like here it just is a surface with the fire spread and flame length, but also very complicated cases where you can see, for example, how the evolution of a fire within a complex compartment. So what we did, we start looking into CFD simulations. At first, what we wanted to do is to see if we could reproduce the experiment just carried out using FDS. So we defined the compartment, 10 by 10. We used like a mesh, which was like 10 by 10 by 10 centimeters within the compartment. Within the smoke extraction, it was more refined because it's very important to model have enough cells within the extraction. Then geometry, leakages, opening, boundaries, and the fire is all designed according to what we see experimentally. So I won't go into the detail on all the different settings that were set up within the compartment, how we modeled the doors, how we modeled the leakages, how we modeled the fire. But in general, in this compartment, we have the big common area two corridors with two different doors at the end of the corridor, two rooms, one with a fire-rated door and one with a smoke-rated door, and also at the end of the corridor there is another room but without door. So, and today, because of time, I'm going to present one of the experiments that I think is very representative, very interesting for see the potential and also the outcome that it can come from these simulations. And this is the case study number 2. The case study number 2, you can see here with all the different, all the different sensors that were placed, but mainly is the case when you have a fire screen, that it will be here, you can see here, the fire screen, that it was taken down at 90 seconds, which was meant to be the time for the fire alarm to be triggered. At 0.9 meters above floor, we have an extraction system which is meant to be constant, 7 cubic meters per second, with an extraction system that have 3 openings here in the common area. We have a smoke extraction opening that I just mentioned, and then we have 4 inlet openings, which is 1 is here, 2, 3, and also 1 here. So what happens if we run the simulations? So you can see here, this is the simulation, the initial one, where we have like the fire, here's the couch and the corridor. And what you can see, if I start the simulation, at the beginning we start having some smoke within the compartment. Then the smoke starts filling up the corridor, the 2 corridors. Then the smoke screen is activated. And when the smoke extraction is activated, you can see that this evacuation route is mainly cleared. So the extraction is enough and the fire screen is enough to keep this evacuation route clean. But you can see the other evacuation route is full of smoke. And also we have spillage within the room without a door. What is important also here, you can see the other 2 rooms that are adjacent to the common area are free from smoke, because mainly I'm going to describe now about what happened in the compartment. So if you look into, for example, results, here I show like temperatures, different temperature, pressure, and also different temperature. I'm going to discuss quickly what it is. So here you have the dashed lines that are like, I know that is pretty small text, but you have the dashed lines and the continuous line, which is the comparison between the simulation and the experiment, what was measured in the experiments. You can see there's a pretty good match of the temperature evolution within the compartment in a thermocouple tree, which is just an array of thermocouples placed in the same position. Here, what is very interesting, you can see here, these are 2 thermocouples, which was placed one in the corridor, which was this corridor, and one inside this room. And you can see that the simulation is very good at predicting how mainly the smoke travels within the compartment, because you clearly see how the temperature would rise because of smoke movement. Also, what is key here is also the pressure within the common area, because what happens when you have a fire inside a compartment which is enclosed, you start having a pressure peak and a pressure increase, because mainly the gases want to expand, but they don't know where to go. But once you have an extraction system, like this one, what you can see at 110 seconds, when it was activated, you start having an under pressure, because an under pressure is made you start removing air within the compartment, so they start having an under pressure within the compartment. And this creates a way that mainly, if you have an under pressure within the fire compartment, there is no smoke that will go through leakages, mainly going through the 2 different doors that are adjacent, that would lead to the 2 different rooms. And also another very important thing is that the heat balance within the compartment. This is mainly, I'm plotting the temperature measured inside the extraction duct. So there was a temperature within the extraction duct, and what is important is that by energy balance, we know we have some heat that comes from the fire, and we have some heat that is removed from the compartment because it goes into the hot smoke. And you can see here we have a good match within this temperature, so this means that the temperature that are extracted from the compartment is also well predicted. All this information comes from, of course, not a trivial process, that you have to do a lot of understanding and how you have to set up the simulation to get good results. Because what is one of the most important aspects is that there are some uncertainties into the data that you would feed the model. And the main 2 that I showed for the case I showed today is the fire, so is the couch, and also the extraction system. The extraction system, the experimentalist told us that they set a frequency that would allow a constant flow rate within the compartment. But this is an assumption, and that since the flow rate is a very big player within the problem, it's very important to have an accurate evaluation of the volume flow rate from the extraction system. But also another important aspect is the fire heat release rate, because what I showed you earlier, this case is a fire that is this couch that is tested in a calorimetry hood. So it's a hood that is a laboratory system with a hood that with an extraction rate. So you have plenty of oxygen in this case, and then all the smoke is immediately extracted from the laboratory area in order to quantify the heat release rate. But what is important, you can see here that the conditions in the laboratory and the condition in the compartment were completely different. Because here you have plenty of oxygen, all the gas flows, they go vertically into the hood, while here what you start having? You start having the walls that they heat up around the couch, you start having a smoke layer that radiate into the couch, you start having different flames, so mainly the boundary conditions around the couch burning are completely different. So assuming that the couch will burn in exactly the same way as in the laboratory is a very big assumption. And this you can see because if I just use the heat release rate curve evaluated in the laboratory, what you can see here, you start having some problems. Because if I do a blind simulation just using the data that it was given by the experimentally, the theoretical values, you can see that you start having problems that, for example, the temporary evolution of temperature is slightly different. Then here the transport of smoke is slightly, different. The pressure is pretty good because we can understand that by the pressure the volume flow rate from the extraction system was actually correct. But also here you can see that the difference in temperature within the smoke extraction system is definitely different. And this means here we are not having any more energy balance, but actually the amount of heat we are extracting in the simulation, the continuous line, is much lower. So we are like storing more heat inside the compartment, and this means that most likely the fire was burning in a stronger way in the case of the compartment for the reason I also mentioned. And doing the simulation of all the cases, we got into many other uncertainties that made the simulation even harder. The first one is that, as I just mentioned, the actual fire heat release rate during the experiment compared to the case of in the laboratory conditions. Then the actual smoke extraction rate I just mentioned, and also what was the actual volume flow rate when they were actually measuring the pressure within the compartment. You have a sort of two-way system that would depend on the pressure itself. So another big uncertainty. And also, how does the sprinklers affect the heat release rate of the fire within the compartment? Because the heat release rate is a key variable within the simulation. And how does the sprinkler affect that? And it's not a matter of how does it set. We know that it would extinguish the fire, would cool down the gases, but what are the data? What are the quantification of this value, which is very tricky and very challenging to define in a simulation, because you need to put this concept in a number. So just to give some take-home messages is mainly that the CFD simulations, so it's very important to properly designing and performing experimental campaigns, in particularly using various instrumentation. So it's very important to understand which type of instrumentation we need, the location, direction, and density. And also it's fundamental to properly characterize the main governing parameters. And for the case I just presented, is mainly the fire heat release rate and extraction rate within the compartment. So CFD simulations are a very powerful tool to study and analyze fire dynamics in multi-compartment facilities. But CFD validations and simulation could be very tricky and challenging, even for trivial cases. Then also is fundamental to be aware of the setting of assumptions, because what I always try to understand and try to communicate is that CFD is a tool that you can use to understand how different settings and different conditions would change the case, but you cannot use and rely on CFD simulation to understand what is going on. As an engineer or a firefighter or as a fire safety engineer, you should know already a priori what is actually the outcome that you should get. So it's important to understand to know the problem well, comprehend the governing parameters and its uncertainties, and then understand what you can get out of the safety simulation. Not just do blind simulation and try to get an understanding. Because as humans, as engineers, as firefighters, we should already know what is sort of the expected outcome we could get. Of course, not an exact number, but more or less what happens. So before... Yeah, before moving to the other part of the presentation, where mainly we started from these conditions, we use the tested conditions in laboratory conditions, and then we extrapolated in a more general setting, when you have, again, a common area, which is more or less the same size, is 130 square meters. We have 3 rooms adjacent to the common area, 3 rooms adjacent to an evacuation route with a corridor. And what we look into, start looking into all different scenarios, how the scenarios would affect the fire dynamics or the outcomes that I just mentioned. Particularly look at how the doors would affect this, if the door are open, closed, if the door leakages, if you use mainly a smoke-rated, fire-rated door, what would be the outcome of it, the compartment openings and leakages, the ceiling height, common area size, fire heat release rate, smoke extraction system, and also ventilation system. And this here in gray, you can see, for example, the baseline case that we presented. So this is, for example, the first example of how doors would affect this. So this is in the top left, we have a closed door, open door for 30 seconds to allow evacuation, and open door during the whole fire event. What you can see between the 3 different simulations is that in the case of closed door and open door for 30 seconds, you start have collection of smoke within the fire compartment. Then the smoke start propagating to the common area because you have a pressure build-up within the compartment, and the smoke starts spilling inside the common area. But what you can see, if you have an open door, the smoke starts spreading everywhere pretty quickly. And this is related to a very important aspect, because open door would have not an effect only on the smoke, but it would also have an effect on the oxygen supply that you would feed the fire. So this is the dashed line. The dashed red line is the heat release rate curve that I imposed in FDS, in the simulation. And you can see in the case of closed door and open door for 30 seconds, at a certain point, the fire drops, because mainly it's an extinction model, so the fire doesn't have enough oxygen anymore to burn, so the heat release rate drops because you don't have enough oxygen. And while if you have an open door, you can see that the yellow simulation is following the dashed line, so there is enough oxygen so the fire can burn according to the curve that I just imposed. And if you also look into the pressure within the compartment, if you have a closed door or open door, you have a very big pressure peak, up to 100 Pascal within the compartment. While if you have an open door, you have a smaller pressure peak, but this is again as an influence on the pressure peak, as the pressure peak would influence the smoke movement, but also having a door open or closed would also influence the fire, but have more or less oxygen within that. The other thing that I wanted to set of simulation that I wanted to present is that what happens if you start having different openings within the fire compartment. In this case, if you have a small hole within the compartment, an opening which represents a small window, or a big window which is like 0.5 square meters. What you can see again, you can see that in the case of a small hole, you're going to see that, okay, the door is open for 30 seconds, you have a bit of smoke that would propagate inside the compartment, the common area, and then if you have a small hole, then the smoke will start spreading inside the common area because you have pressure build-up within the fire compartment. While if you have an opening, even if it's a small one, what you can see, you start having not smoke spillage inside the compartment. And this is mainly related to what I can see. You can see here, you can see that if we look into the pressure evolution, in the case of a small or a big opening, the pressure build-up inside the compartment is much smaller, so the smoke doesn't have enough inertia and enough push to get pushed inside the other compartment. And in the case of having a small hole, you start getting again the 100 Pascal pressure peak within the compartment. While what I want also to mention that we have to make sure and pay attention that when you open also openings and windows within the fire compartment, you can see here, window, yellow simulation. Again, you go into under-ventilated conditions, so the sort of heat release rate drops. But then what you can do, you can see is that if you have a window, you also provide oxygen to the fire. So you would allow the fire to also burn longer, bigger, compared to the case when you have a small hole, but then you will have a pressure peak, so the smoke will propagate inside the other compartments. And what is very important is these simulations, we didn't consider any wind effect at the openings. So this is a very important aspect, because if you have, for example, a big facade, when you have like a big wind-induced pressures on the facade, this would have, of course, an influence on how mainly the gases and the flows would enter or leave from the opening. So this is a big assumption, but we have to be aware, again, CFD simulations, you make some certain assumptions, but pay attention that this may be a very important aspect. And then what we did also, we look into other different aspects, door leakages, ceiling height, common area, fire heat release rate, and moisture extraction system. And because of time, I'm not going to present today because it takes a lot of time, but mainly you can see that varying all these variables, you can have a different evolution of the fire and the smoke within the multi-compartment facility. Last aspect that I wanted to mention is, because we focus a lot, is the influence of ventilation system within a multi-compartment facility. What you can see here, what is important also to state here, all this study has been done by having a steering committee that made of different experts in the fire safety engineering field, firefighters that would suggest us, or architects that would suggest us what are a sort of common configuration that we could expect in a common building. And these are three different configurations that we find in multi-compartment facilities with a ventilation system. So this is the supply, this is the extraction, and you can see I have three different cases. The first case is independent supply and extraction. So we have a supply and extraction the same for the common area and the corridor, but we have extraction and supply independent for each room. Then here you start having the common extraction for all the different compartments, but independent supply, and then finally you have the extraction and supply which is common for all the different compartments. Again, we want to CFD and we start looking into setting common simulations with the settings that were like suggested from the common practice. We look into how, so you can see here, this is the case of configuration 1, independent supply and extraction. What you can see again, we have a fire in the room. The fire starts increasing, the door open for 30 seconds, you have a bit of spillage of smoke inside the common area, but you can see that the smoke mainly stays within the compartment. And at a certain point, you can see that you start having smoke spillage inside the common area because you have overpressure within the compartment again. But all the other rooms are sort of safe because you don't have smoke spillage through the ventilation system. What is interesting that I'm going to discuss briefly later, you can see here the CFD simulation, sometimes you can have a bit of weird results because mainly you don't have enough oxygen within the compartment, so you start having a bit of combustion at the openings, which is a bit of weird results, but I'm going to mention a bit later what this means. And again, if you go into the results, you see, again, heat release rate, trying to follow always the same curve under pressure conditions, peak of pressure peak, which is relatively small, within 20 Pascal. But then if I look into, these are thermocouples within the extraction system in the supply and the extraction system in the extraction, you can see that the temperature, there is no temperature rise because mainly there is no smoke traveling through the ventilation system. Another aspect is that what happens if you start having extraction that communicates within all the different compartments. And in this case, we moved the compartment all the way to the end of the extraction system because it would represent a more challenging situation because all the other extraction branches would be along the smoke extraction path. You can see again here that you have a smoke spillage because overpressure inside the compartment, because smoke spillage within the corridor, but there is no smoke spillage within the different rooms and also the common area. What you can see here again, under ventilated conditions, because we have a room, then we have relatively small pressure peak. But then in this case, if I look in the thermocouples in the extraction system, you can see there is some smoke that goes into the extraction system, because mainly the extraction system communicates with the fire compartment. Then the problem comes when we have configuration 3, where we have supply and extraction all connecting all the different compartments. What you can see here, again, we have fire within the room, then a bit of smoke going because of the open door, but then you start seeing here the compartments ahead of the ventilation supply, mainly the smoke, because of pressure, goes into the ventilation system and then starts spreading in the other compartments. As you can see, this will be a very dangerous situation, because mainly if you don't turn off the supply, then you start having smoke spillage, not just in the fire compartment, but also in the other compartments, which would be very challenging. For example, if you have a stay-put strategy, that mainly you start sort of intoxicating all the people in other rooms, thinking that is actually a fire compartment, so you shouldn't have smoke spread in other facilities. And just in line what I just mentioned, now you see temperature and smoke traveling along the ventilation in the extraction, but also smoke traveling along the supply that would spill in other compartments. So we start thinking about how can we solve this? Can we solve this by, again, opening a window? Within that, again, we have to be aware that a window would provide some oxygen to the fire, but also will sort of release the pressure peak within the compartment. So you can see here, since you reduce the pressure within the fire compartment, now the smoke is not able to travel along the supply because it doesn't have enough. Mainly, you can see here, you have, like, again, under ventilation, the pressure peak is smaller. You have smoke that travels along the extraction, but not smoke that travels along the ventilation supply. The last case I wanted to present is that talking to the steering committee, some of them argue the fact that you might have some fire dampers within the ventilation system. So fire dampers that would stop the fans in the case of a fire alarm. And you can see here, if you have dampers and the stop, and then you have our window, you can see that the smoke would travel inside the ventilation system and supply, but would not be able to, again, because it doesn't have enough pressure. You have a lot of pressure losses due to friction within the ventilation system, and it's not going to spread in the other compartments. And this is clearly seen that you see a bit that it travels within the ventilation supply and extraction system, but the pressure peak is very small, so the smoke doesn't have enough energy to make it to the other compartments. Just to wrap up, some messages that I wanted to give from today is that CFD simulations are a very powerful tool for parametric studies, but it's very difficult to rely on absolute values. So what I showed today, I didn't give you like any comment of having 250 or 300 degrees, because we're always talking about qualitative data and qualitative analysis, because we try to understand if you change a certain parameter, what would be the effect on the problem that we are studying. It's fundamental to be aware of the settings and assumption at the base of CFD simulations, to know the problem, comprehend also the governing parameter and uncertainties. And I show you in test number 2 that I presented today, what was fundamental is the fire within the compartment, but also the extraction, because there are 2 main governing parameters for this case. There are some large uncertainties in FDS in the case of under-ventilated conditions, what I mentioned you when you start having flames outside the window. And what I would like to advise is that in the afternoon, there is going to be a very interesting breakout session looking into this specific problem and the smoke propagation in buildings, simulation based on experimental research by Pim and Ruth, that will discuss also a bit about the under-ventilated condition in multi-compartment facilities. Different fire safety measures can be more or less effective for limited smoke spread in multi-compartment facilities. Ventilation system can be hazardous in multi-compartment facilities. And then also the VIPA-3 numerical study was used as a basis from a framework for the evacuation strategy in healthcare facilities. As you can see today, I didn't have time to discuss about that, but hopefully next year we'll discuss about the framework that came out of this numerical study. All the information I presented today are available online open access. This is the report in Dutch that you can read and mainly discuss about what I presented today. Taking pictures. Finally, I would like to acknowledge the VIPA, the sponsor, the Flemish Institute for Fund for Person-Related Matters, my supervisor, Professor Barmercy from the University of Ghent, Professor Beiji, Engineer Poppe, Anne Bessen, all the VIPA Free Steering Committee, and also all the students and colleagues that I collaborated, shared some years during when I was at UGent. Finally, I would like to thank you for your kind attention, and I'm here to answer any question or during the coffee break in the afternoon barbecue, whenever you want. Thank you.
Okay, time for questions. The idea was, like in previous conference, to throw a microphone, but as I said, we don't talk about football, and a Belgian throwing a ball in would not work. So we have a microphone for those who have questions. So don't be afraid. Who dares? Okay, good.
Hi, my name is Mere Veerman. I'm from Royal Hagen DV. I'm a fire safety engineer. My question is about the leakages. How do you determine the type of leakages, and do they vary with... kijk, you're prepared for this question.
Yeah, that's... so what happened is, as you mentioned, is the leakages are a very important parameter for when you look into smoke spillage. So what happened before running all the experiments, it was carried out according to the standard blow door test with a 50 Pascal pressure increase within the compartment, and according to different theories, it was estimated the leakages at the compartments, so all along the walls, at the doors, single door, small doors, and also here is the difference between, a fire-rated door, 72 centimeters square, and 3 centimeters square for the smoke-rated door. So this was implemented, it was at the base. I didn't have time to go into all the details, but it was estimated according to the standard.
Thank you.
You're welcome.
Okay, next question. I think yeah.
So thank you, Andrea. I have a small question relating to how sprinklers would affect the pressure buildup in such a compartment. What did you see?
This is strange. Okay.
Okay. No, I mean, what I can say is that at Ghent University there is a lot of research going on the effect of any extinction system on the fire dynamics. What I can say is that FDS is still, and all these simulations are still a bit behind, because there is still a lot of knowledge that has to be developed in understand, particle size, particle distribution, and what are the effects. What I can say is that in theory, if you have a sprinkler that would activate, it would be located, I have to go a bit behind, but it would be located above the couch. So what you can expect first, if the sprinkler activates, it would significantly reduce the heat release rate of the fire. Therefore, you would have a much smaller pressure peak. But also what a sprinkler would do would also reduce the temperature of the gases within the compartment. So again, tackling down the pressure peak within the compartment. So it could be used as seen as if works as a similar solution similar to the opening a window, for example, that would reduce the pressure peak, so avoid smoke spillage into adjacent compartments.
Thank you.
You're welcome.
Yeah, Ruud. Yeah.
Okay, thank you, Andrea. Very nice work that you did. Ruud van Herpen, Eindhoven University. A question related to the question that Mir asked. You showed us the equivalent leakage area.
Yeah.
But the equivalent leakage area depends on the pressure difference between. Is it a constant factor, a constant opening, or is it also depending on the pressure in your case?
Yeah, that's a very good point. Thank you for the question. So mainly, what you have, according to the standard, you impose a constant pressure increase, which is 50 Pascal, and actually highlighted here. But what I showed you earlier, we had pressure peaks of 10, 20, 100 Pascals within the compartments. And, this solution would definitely change if you have different pressure increase. Because what you can see is that if you have a bigger pressure increase, small holes or leakages could open. So this is a value, and it's assumed constant based on this pressure increase, because these are the information we had. But I would expect that these leakages would increase if you have a higher pressure increase within the compartment, yes. But in FDS, in every simulation, usually you have to give a number again, and this is the information we had, and I believe it's better to use something defined according to the standard rather than just throw some numbers.
Okay. Yeah.
So I have a question. Thank you for your presentation, very clear. I was wondering, why is it so difficult for these simulations models to impose the wind? Because can't you just impose a counter pressure on the window or whatever? So why is it so difficult to take it into account? Easy question.
Another easy question. Thank you very much for the question. But in general, it's not hard, and it's something that I didn't present today, but we did the study, that we sort of assumed a constant flow velocity, horizontal to the floor, that it would go into the facade and create like an overpressure. We saw there is definitely an influence, but then it's like, okay, which sort of wind speed you would impose? It's something you can do easily, but would you use 5 meters per second, 10 meters per second? And of course, by using a certain speed on the facade, would have a different pressure exchange at the window, and therefore you would have like a different effect on the pressure peak. But what you can see is that if you have enough inertia or enough wind speed and momentum at the window to not let the gases to leave from the compartment, then you would have the same effect having a wall. Yeah. And also, you could also go into the case that you start blowing oxygen inside the compartment, and you start sort of like feeding the fire with the fresh air that loves it if it wants to burn.
Okay. Any further questions? Okay.
Hello, good morning. My name is Franklin. So my question is, I did not see where you mentioned about sensitivity analysis, because at the fire source, you can also maybe use finer mesh, and it could probably give different results. And my second question is, how did you deal with pressure buildup when you simulated the smoke extraction? Thank you.
So regarding the first question, what we did, and it was also part of the sensitivity study of scenario study, you can see here, we look into the fire heat release rate. So for example, we used this couch that I was testing in the laboratory, which was a medium alpha T squared with about 800 megawatt as a peak heat release rate. But also we start looking into fast fires. And I didn't present today because what you have, if you have a faster fire, since you have a bigger rate of change within the compartment gases, you would end up in a bigger pressure peak. And also, since it grows faster, it would also have all the same problems I just presented today earlier in time. And the second question was about the pressure buildup within the smoke extraction. And what we did is FDS look into different, is a buildup, is a key parameter pressure within the compartment. So what they have, you automatically measure it based on the heat release rate and extraction. What we had, we imposed an extraction rate according to a certain speed and a volume flow rate at extraction. I don't know if I have something here. It's a bit hard to go back, but mainly we impose a flow rate, and the flow rate will directly have an influence on the pressure buildup, because mainly you start not having this pressure buildup anymore because you start removing air from the compartment. Therefore, you're reducing the pressure buildup, because mainly the air that it wants to, you can see here, the air that it wants to expand within the compartment and that it creates overpressure mainly start being removed by the extraction system. So this one of the big advantage is not just removing smoke, but also limiting the pressure buildup inside the compartment through the ventilation system, the extraction system.
Okay, I think, yeah, I cannot, I cannot refuse you.
You are very kind. Peter van der Leur. I liked your statement about the difference between parameter studies and absolute predictions. Would you go as far as to say that the predictive value of a CFD simulation is small?
The
The predictive capability of a CFD simulation in cases where you don't have measurements to validate against.
So what I would say is that it depends if you use for profession or you use for research. So today I presented the research that we have some laboratory experiments. I will try to reproduce what happened in the laboratory. What I showed that I wanted to show and make you understand is that if you don't have a good understanding and quantification of the key variables, which means, as I mentioned, the volume flow rate and the fire, actual fire within the compartment, because we quantified the fire within the laboratory, but the conditions were completely different. So most likely the the heat release rate curve will be different. So it's important to understand these quantities. But then these quantities are fundamental. And the fundamental quantities would give a good understanding on the values within the simulations, because if you get the good quantities of governing parameters in a good way, you would at least get more or less the order of magnitude of results. If you look at instead in the profession, what you can see, I think that is a very powerful tool, as I mentioned, but we need also expert users that are aware of if you impose a certain heat release rate or if you impose a certain leakages, what are the assumptions behind it, because it's very easy to plug in some numbers and get results, but it's important to understand, particularly if you do a project, the building is not there, it's not been tested, to understand if it makes sense and it would be reasonable to have that results, because you cannot use this tool blindly, because it's very powerful and you can go also easily into big mistakes if you don't have at least an understanding what's going on or what might happen within the compartment.
Okay, I think we now have to conclude this session. Thanks a lot, Andrea. I had a long list with questions, but you did it very well.
We can discuss later or we can discuss around the conference. Thank you very much.
Thank you very much.